Okay, let's unpack this. We've all been, justly impressed by modern AI. It can deliver results that feel almost like magic sometimes.
Absolutely. Solving complex problems, generating text. It's quite something.
But there's a crucial, really fundamental difference between an AI getting the right answer and an AI proving exactly how it got there.
And that difference, well, it's now defining the legal, commercial, and ethical limits of AI deployment. In the real world, that is.
Right.
This whole deep dive actually was spurred by an incredibly sharp question from you, the listener. A really pointed question.
Yeah, it cut right to the chase.
It did. Show me the exact data you used to make that decision with hardware proof.
That sounds, well, deceptively simple, doesn't it?
It does, but the sources tell us it instantly crystallizes this entire multi-trillion-dollar problem of AI trust.
You're essentially demanding that the AI follow the first rule of math class.
Precisely. If you can't show your work, you just hand in the final number.
You get 0 points,
Yeah.
even if the answer is right.
Exactly. 0 points. That simple, kind of unforgiving rule, it applies perfectly here to the AI transparency problem.
So our mission today is to explore why current AI struggles so much to show their work, what the huge stakes are for critical applications.
And yeah, what researchers are actually trying to do to fix this black box that holds all the answers but won't explain them.
Okay, so let's start with those stakes, because our source material makes a really crucial distinction here. It basically splits the field in two.
Yeah, it's like we're living in a two-speed AI world right now.
Explain that. What are the two speeds?
Okay, so on one side, you've got what they call best effort AI.
Okay.
This is the system usually built on these massive transformer models, right? It functions like a brilliant student who somehow aces a complex calculus problem.
Wow, okay.
But when you look at their worksheet, it's completely blank. Their performance is just astounding, uncanny even.
So peak performance, amazing results, but the process, totally opaque, non-existent.
Correct. And in high-stakes fields, think medicine, defense, high-frequency finance, that impressive performance can actually be, well, worthless.
Worthless, really.
In terms of accountability, yes. Which brings us to the second category, verifiable AI.
Ah, the contrast.
This is the student who gives you the correct answer and the rigorous step-by-step mathematical proof.
Shows their work.
Shows all the work. And this is the only kind of work that has sustainable value in those critical applications we mentioned.
But hang on a second. If a best effort AI is, say, 99.9% accurate at spotting financial fraud or predicting when a machine needs maintenance, doesn't that sheer performance outweigh the lack of an audit trail? Especially in many commercial scenarios. Why would a big company care about the blank worksheet if the result is highly profitable and effective?
Because accuracy is only one side of the coin. Admissibility, or maybe defensibility, is the other. The consequences of getting 0 points here are severe. Legally, think about it. An AI decision you can't trace back to its inputs and calculations. It's simply inadmissible. It's indefensible in court.
So if there's a dispute, you've got nothing. You can't justify it. You can't prove it wasn't biased.
Exactly. The system can't survive a challenge. And commercially, it becomes virtually uninsurable and therefore unusable for serious enterprise applications.
Right. Who's going to underwrite the massive risk?
Yeah.
Like an autonomous vehicle or a diagnostic system, they can't fully audit if something goes wrong?
Precisely. The whole future of high-stakes AI has to be built on this foundation of deterministic proof. Because without it, the system just can't be trusted, it can't be audited, it can't be corrected when, and it's always when, not if an error happens.
Okay, so if the stakes are that high, why can't the AI just open its digital ledger?
Yeah.
Show the work. It's a machine, right? It must have recorded the steps somewhere.
You'd think so.
What's the technical hurdle? Why the opacity?
This is where we run smack into the black box problem. And the sources offer a really great analogy here.
Okay, let's hear it.
Asking for the exact data and the hardware proof behind an AI decision. It's like asking a master chef for every single grain of salt they used in some complex sauce.
Okay, every grain.
And the serial number of the specific stove burner where it was cooked.
Right. It sounds like demanding information that's just functionally irrelevant to the actual decision, or at least impossible to track.
It is, pretty much.
Okay.
Because the core technical issue is how these modern large models, like transformers, actually learn and operate. Decisions aren't made using neat, easy-to-follow if-then rules.
No simple logic tree, then.
No, they're probabilistic. The final output emerges from literally billions of parameters interacting through countless layers of matrix multiplications and these complex attention mechanisms. It's a web.
So the knowledge isn't stored in nice little files we can just look up. It's
Yeah.
spread out, decentralized.
Exactly. It's what some researchers call smeared knowledge.
Smeared knowledge, okay.
Think about that single grain of sand. Maybe a specific fact the AI learned from one Wikipedia article way back in its training data.
Right.
That fact doesn't sit in one neat little memory location. Instead, it influenced numerical weights across the entire model. It gets diluted, smeared out among trillions of other influences and connections.
Ah, okay. That clarifies why the training process itself basically destroys individual traceability. It's like trying to find one specific drop of blue paint you use to mix a giant vat of purple paint.
That is the perfect analogy. During training, especially with techniques like gradient descent, individual data points just lose their discrete identity over millions and millions of tiny adjustments.
You can't unmix the paint.
You cannot unmix the paint. You can't trace that one drop of blue back to its original bottle. The information is fully integrated, distributed, transformed into this complex web of probabilities.
And then there's that other part of the listener's request, the hardware proof. That's even more specific.
Yeah, that's part the sources call absurdly granular.
Absurdly granular.
Trying to trace a high-level decision like, should we approve this loan, or is this image cancerous? All the way down to a specific transistor firing or a specific memory address that executed one tiny part of the calculation. It's functionally impossible for real-time accountability.
But why ask for it then? Is it just theoretical?
Well, the sources note it's not just philosophical, it's often driven by very real supply chain security concerns.
Security. How does the hardware trace connect to security?
Think about regulators or companies deploying AI in critical infrastructure. They want to ensure that a vital calculation hasn't been compromised by insecure or maybe even faulty silicon, fake chips, hardware trojans.
Ah, so they want traceability beyond just the software code, but right down to the provenance and integrity of the hardware itself.
Exactly. It's a complete system accountability request. And current architectures, they just weren't designed for that level of deep introspection, not even close.
Okay, so if we can't unmix the paint, we can't get that fundamental deterministic proof that show your work. Does that mean the problem is just completely unsolved? Are we stuck?
Not entirely stuck. This is where we move into the realm of approximation, or what we've kind of dubbed partial credit.
Partial credit. Okay, like in school again? Better than 0 points.
Better than 0 points. Researchers have gotten very clever, actually, in developing these post hoc explanation techniques. They give us a glimpse inside the black box.
A glimpse, so not the full picture.
No, they can't guarantee the how, the exact causal chain, but they can often estimate what the model focused on, or maybe how much a certain input contributed to the final output.
Okay, so what are the main tools they're using for this partial credit approach?
Well, there are 4 major techniques people use right now. First up, attention visualization.
Okay, attention.
This is kind of native to transformer models. It shows which parts of the input text the model paid attention to most. So if you ask the AI about the grain of sand, the visualization might light up and highlight that phrase.
Showing it weighted heavily.
Right. It shows what it looked at, but...
Not necessarily why it drew the conclusion it did from looking at it.
Exactly. That's the limitation. Second technique, saliency maps or feature attribution. These use methods you might have heard of, like SHAP or LIME.
Jam and lime, right. Heard of those?
These algorithms try to estimate the quantitative influence, like how much each word or pixel in the input contributed to the final decision.
Okay, so that sounds more useful getting actual numbers.
It can be, but I remember the sources warning about this too. While these methods are often honest about what the model used, they aren't always helpful for a human auditor who's trying to verify actual understanding or reasoning.
Right, there was that famous example, wasn't there? The wolf picture.
That's the classic one. The AI was trained to identify wolves, did it really well, but the saliency map highlighted snow in the background.
Not the wolf.
Not the wolf itself. The explanation was perfectly honest, technically. The model was using the white background as a strong signal because wolves often appear in snowy pictures in the training data.
But useless for checking if the model actually understood wolf. It just understood things usually found with wolves.
Precisely. It demonstrates that weakness of relying on correlation, these statistical patterns, rather than proven causation or understanding.
Okay, so that's attention and saliency. What about looking at the training data itself? Can we trace influence back there?
That's the third tool, influence functions. This uses some pretty advanced, computationally heavy math.
Sounds expensive.
It is. It tries to retroactively estimate if one specific training example significantly swayed a particular prediction later on.
Ah, so you could potentially find if a bad piece of data caused an error.
Potentially, yes. It's extremely valuable for that kind of offline analysis for auditing after the fact. But it's definitely not something the AI can do on the fly while it's giving you an answer. Too slow, too complex.
Got it. Offline auditing tool. And the final method.
The fourth is probing the model. This involves training smaller, kind of auxiliary models.
Helper models.
Yeah, helper models designed specifically to predict what the main giant network knows about certain concepts. You're essentially asking the smaller model to interpret the internal states, the activations, inside the big model.
Trying to see if specific information was actually represented and used internally.
Exactly. Did it account for this factor? Did it represent that concept?
Okay, so it sounds like we have some pretty sophisticated ways to, peer into the black box. Attention, saliency, influence functions, probing. But they all seem to fall short. They don't deliver that original demand. Show me the work, the deterministic proof.
That is the essential truth, unfortunately. These are all approximations. They provide a narrative explanation, sometimes a useful one, which is definitely better than nothing.
Right.
But they don't guarantee that the model is reasoning correctly or based on the intended inputs or using sound logic. And that gap, that forces us to confront some really huge issues around accountability.
Which brings us back to the listener's motivation. This whole challenge of transparency, this lack of proof, it leads to some major implications for how we deploy and regulate AI.
Absolutely. The lack of traceability leads us down this slippery slope. The sources point to about 4 major concerns. First, and maybe most obviously, trust.
Right.
Can users, can doctors, can judges rely on high-stakes AI decisions if the process can't be verified? If the AI can only say, well, I got this answer because of a massive, complex confluence of probabilities, that really erodes confidence.
Yeah. Trust me isn't good enough when the stakes are high. What's second?
Second, accountability. If an AI gives bad advice the self-driving car crashes, the medical diagnosis is wrong, auditing the cause becomes an ethical and legal nightmare.
How do you figure out why it went wrong?
Exactly. Was it a flaw in the model's design? Or was it due to one specific piece of bad or biased training data? Without clear traceability, it's almost impossible to distinguish between those. And knowing the difference is absolutely essential for assigning liability, for fixing the problem.
A legal minefield indeed. What's the third concern?
Third is more of a philosophical angle, but it has practical consequences.
Okay.
If the AI's knowledge is just smeared across billions of parameters, is it truly knowing anything in the human sense? Or is it just incredibly sophisticated pattern matching at a scale we can't even comprehend?
And why does that matter, practically?
It matters because if the system doesn't know or understand in a way we recognize, it challenges the whole concept of assigning responsibility or even culpability when it makes a life-altering error. How do you hold a pattern matcher accountable?
That's a deep question. Okay, so if we can't just keep using best effort AI in these high-stakes, verifiable AI situations, what needs to change? What radical shifts are the sources suggesting?
We basically need to fundamentally change how these models are built and how they're regulated. First, there's a huge push for mandated audit trails.
Digital scratch paper.
Essentially, yes. Systems that meticulously log key inputs, the specific weights involved, the intermediate calculations for every single output, creating that traceable record as the decision is actually being made.
That seems like the most direct answer.
Yeah.
But doesn't logging all that intermediate data create a massive, maybe even crippling data overhead? Storage computation.
It absolutely does. That's the hidden cost. If a modern large language model generates, say, 50 words,
Okay.
logging the potentially thousands of adjusted weights and all the intermediate math for each of those words could multiply the storage and processing cost by like 10 or 20 times, maybe more.
Wow.
We're trading performance and efficiency directly for traceability. That massive economic cost is the often unmentioned burden of truly verifiable AI.
Which naturally leads to the second potential solution. Maybe we need simplified models.
Exactly. We might just need to accept sacrificing some of that peak cutting-edge performance in certain critical fields.
To gain traceability.
To ensure the architecture is inherently traceable, auditable. It could mean intentionally stepping back from a massive black box that gets 99.99% accuracy to a slightly simpler, maybe 99% accurate model, but one whose processes are transparent and provable. Performance isn't everything when lives or legal rights are on the line.
Makes sense.
Yeah.
And finally, you mentioned regulation and research.
Yes. On the regulatory side, there needs to be a real push for show your work standards in critical applications, similar to how financial models already have to be auditable and repeatable in many contexts.
Setting a baseline.
Right. And on the research side, the focus really needs to shift towards explainability by design.
Explainability by design, meaning
Building models from the ground up that inherently produce human-readable reasoning chains right alongside the answer. Instead of building the black box first and then trying to reverse engineer an explanation after the fact, build transparency in from the start.
So this whole deep dive has made it really clear. We need to move past just being impressed by the magic trick, the miraculously correct answer. We have to start insisting on the verifiable proof. We need that calculus student who actually shows the steps, the intermediate logic.
And that leads us to the final provocative thought for you, the listener, to really consider.
Okay, leave us with this.
If an AI provides what it claims is the best course of action, maybe in a medical situation or a legal case, but it can only give you that high-level, post-hoc approximation of why, like describing the snow instead of the wolf.
Yeah.
Is that fundamentally any different from that AI just saying, trust me, the answer's 42?
Think about the weight of that trust. The next time an AI system impacts your life, your work, maybe your health, what do you need? Impressive performance? Or do you require undeniable proof?
Something to mull over.
Definitely. Until next time, keep those sharp questions coming.